There are several laws of exponents that we learned about, and it seems like forever ago that we did, but we did them. The first law of exponents, the ones that really kind of hone in and get at it, are the multiply by the same base, add the exponent. So we're going to call this Rule 1, Law of Exponents. We know that if I have base to the x power times base to the y power, then this is equal to base to the x plus y powers. Now, each of these laws is going to have a reverse version for logarithms because logarithms are the inverse function of exponential functions. So we'll call this next one reverse 1. And reverse rule 1 says that, well, let's take this expression, the log base 2 of x. And this means that the exponent that I would take 2 and make it x, or the exponent that I would use to raise 2 to get to x, plus then we have the log base 2 of y, which is the exponent that I would use to raise 2 to get to y. So the two of those together, think about this as adding exponents. And adding exponents is sort of like what's happening here, where I'm adding exponents. I'm adding two exponents together. And when I add two exponents together, it's really like I'm multiplying their bases. So what ends up happening is that this is the same as the log base 2 of xy. And I want to show you an example of this because this is tricky. This is really tricky. This is sort of a massive deal on how to combine logarithmic expressions. So let's change colors here. And if I take the log base 2 of 8 plus the log base 2 of 4, well, the log base 2 of 8 is 2 raised to what power is 8? That's 3. 2 raised to what power to 4? That's 2. This is equal to, well, 3 plus 2 is 5. This would be the log base 2 of 35. So in the end, when I add logs of the same base, I multiply their arguments. And that's what I'm going to write in here. Add logs of same base, multiply their arguments. So this is the first of 3 major laws of logs that we're getting to. And there's a way that this should actually make sense to you. Because this is going to be tricky math for a little bit until you get at the nitty-gritty of what it's really saying. Because this is basically saying the log base 2 of 2 times 2 times 2. And you're adding the log base 2 of 2 times 2. And so what this is kind of expression is pointing to is that there's 3 2's there. There are 2 2's there. And if I take the sum of those, there should now be 5 total 2's. So 2 times 2 times 2 times 2 times 2. And that gives me 5 2's. But the effect of that is that you're actually multiplying the two of them together to get the additional 2's. So spend a little bit of time on that one. Let's go now to rule 2. Rule 2 is that if I have 2 to the x over 2 to the y, that's equal to 2 to the x minus y. The reverse of rule 2 is that if I take two log expressions of the same base, log base 2 of x minus log base 2 of y, and I subtract the 2, then I get the log base 2 of x over y. That is reverse 2. That's a bigger picture. Now, note that this does not mean, there's a big misconception that can happen. This does not mean that the log base 2 of x minus the log base 2 of y is equal to the log base 2 of x over the log base 2 of y. That's not what that is. That's not the same thing. So just be careful of that. This is a big no. That's not true. What this does mean is that if I have the log base 2 of 14 minus the log base 2 of 7, that's equal to the log base 2 of 14 sevenths, which is the log base 2 of 2, which is 1. That's what in essence this is doing. So That's a big one, and we're going to kind of work with these two rules here for a second before we branch over into something different. I want you to, let's first write as a single log. So this is going to be a subset of problems where I say write as a single log expression. So if I want to write these as a single log expression, we'll start with the simple one, the log base 7 of x plus 1 plus the log base 7 of 4. And writing these as a single logarithmic expression means merging them so that it's the product of the arguments. This would be the log base 7 of 4 times x plus 1, or you can write it as the log base 7 of 4x plus 4. Okay, we'll call that part A, and then I'll do a part B here. If I want to do another one, let's do the log base 7 of x plus 1. Then we're going to do plus the log base 7 of 4 minus the log base 7 of 8. So what's happening here is that two of them are being added and one's being subtracted. And if I bring this all together, the two that are being added are being put as multipliers, 4 times x plus 1, and the one that's being subtracted becomes a divider, minus or over 8. And we could actually simplify this as the log base 7 of x plus 1 over 2. Okay, this also can manifest itself in some solve problems. So let's do some of these where I'm going to ask you to solve the log base 7 of x plus 1 plus the log base 7 of 4. And that's going to be equal to the log base 7 of 8. So here's a solve problem where solve means just find the value of the variable that makes this true. What you can't do not do this. Do not just pretend that we're just going to drop all the logs. This will be something that's very lazy and very inclined to you're not thinking about what's happening. This is not a true statement. You can't just divide by log or any of these other things that people say that they want to do. What we have to do is we have to take the left side of the equation and combine it into a single logarithmic expression as we've been doing right up above. The log base 7 of 4x plus 4. And that's equal to the log base 7 of 8. So log base 7 of 4x plus 4 equals the log base 7 of 8. Now we can drop the logs because we have the two arguments themselves are equal to each other very clearly. And I can say 4 times x plus 4 is equal to 8. So 4x equals 8, or x is equal to 2. Oop, kidding. This should be 4x is equal to 4, and x is equal to 1. Okay. Continuing on, let's talk about the third rule of laws, of exponents first. Rule 3, b to the x to the y power equals b to the xy. Power of powers rule is what this one is. And the reverse of this is really, really, really tricky. This is reverse 3, and this is my favorite of them because it makes things a lot simpler. This reverse acts like this, and I want to show an example before I get to the rule here. I know that the log base 2 of 35 is the same as the log base 2 of 2 times 2 times 2 times 2 times 2. 5 2's. This is counting 5 of them. This is the same as the log base 2 of 2 to the 5th power. But I note that if I actually took all these and broke this up, this would also be the same as the log base 2 of 2 plus the log base 2 of 2 plus the log base 2 of 2. I'm going to write this 2 more times, so bear with me, plus the log base 2 of 2. It's equal to, well, let me erase this. It's equal to 5 of these. 5 log base 2 of 2's. And I know that that's equal to the log base 2 of 2 to the 5th because that's what this is. So this 5 this power of 5 actually can become a multiplier of the entire logarithmic expression, which is saying that the log base b of x to the a power is equal to a times the log base b of x. This is the rule, and this is the one that is just going to get weird. And this is why people tend to struggle a little bit with logs. You have to really think in terms of exponents. But let's say that I have the log base 10 of the square root of x. Well, that's equal to the log base 10 of x to the 1/2, which is equal to 1/2 times the log base 10 of x. Or if I have the log base 73 of the 4th root of 125, that if I wanted to bring that down to something a little bit simpler, I could say that that's the same as the log base 73 of 5 to the 3/4, or 3/4 times the log base 73 of 5. Okay, I promised you that this was going to get weird, and I need you to bear with me as we explore this weirdness, because there's so much that happens with this. So let's kind of dive into a few more problems. We're going to express these following as the log base 2 of m and the log base 2 of n. Okay, so these are about breaking logs apart. You're going to see things like the log base 2 of m to the 5th times n to the 7th. And breaking them apart as much as possible is what you need to do. Log base 2 of m to the 5th plus the log base 2 of n to the 7th. And these exponents now become multipliers. 5 times the log base 2 of m plus 7 times the log base 2 of n. Next, let's do the log base 2 of m square root of m. There are a couple of ways to tackle this now. One of them really becomes about doing things like breaking this up even more into the log base 2 of m plus the log base 2 of root m, which is the log base 2 of m plus the log base 2 of m to the 1/2, or the log base 2 of m plus 1/2 times the log base 2 of m. And 1 plus 1/2 is 3/2. So this would be 3/2 log base 2 of m. But it is actually far simpler just to take this top one and rewrite this as the log base 2 of m to the 3/2. If you remember that this is m to the 3/2, then that 3/2 can just come out and give you this right away. So however you deal with that, that's a very, very key thing that happens here. And then let's do another one. Let's see how this can really be used to manipulate these expressions very, very well. The log base 2 of, let's go, 16 over m squared n. So what I can do is I can break this apart now and make this the log base 2 of 16 minus the log base 2 of m squared. Note that this n is also in the denominator, so this would also be a minus log base 2 of n. That way, the minuses are acting like division of what the argument's doing. Now, log base 2 of 16 is 4. And I can do 4 minus 2 times the log base 2 of m, and minus the log base 2 of n. And that's kind of as simple as that goes, but that's an expression that works. You have them down to the most simple possible log expressions, log base 2 of m and log base 2 of n. Okay, next direction set are things like, let's say that the log base 7 of 3 is 0.56, and the log base 7 of 2 is 0.36. These would be given in order to help solve a problem. And you would be able to accomplish the next two without the use of a calculator. I'd be asking you the log base 7 of 36 and approximate it. And we'd say approximate to 2 decimal places. So we'd be using what's given up above to kind of process that. I would first do a prime factorization. 36 is 4 times 9, or 2 squared times 3 squared, which is the same as the log base 7 of 2 squared plus the log base 7 of 3 squared, which is 2 times the log base 7 of 2 plus 2 times the log base 7 of 3. And now I'm going to do a substitution because I know that the log base 7 of 3 and the log base 7 of 2 are given up here. So this is really 2 times 0.36 plus 2 times 0.56. And that is 0.72 plus 1.12 or 1.84. Let's do another one. I could do the log base 7 of root 6. So log base 7 of root 6 is the log base 7 of 6 to the 1/2, or 1/2 log base 7 of 6. But log base 7 of 6, if I break up 6 into its prime factors, I get 2 times 3, which gives me the log base 7 of 2 plus the log base 7 of 3, which should be in parentheses because the 1/2 is multiplied by both of them. And that just means that I'm going to add 0.36 plus 0.56, which is 0.92, and half of 0.92 is 0.46. So again, we were able to approximate that log just knowing the other two. Finally, I could do one that's even more challenging. I could do the same direction set. I could do the log base 7 of the cubed root of 1 over 98. And I'm going to show you can actually accomplish this by hand, knowing only those two facts that were given up here. First of all, that third root is actually a 1/3 power. This is 98 raised to the negative 1/3. So then I'm going to get negative 1/3 times the log base 7 of 98. And let's factor 98. 98 is actually 2 times 49. So if I break this up, I get negative 1/3 times the log base 7 of 2 times the log base 7 of 7 squared. The log base 7 of 7 squared is 2. You can move the 2 out in front and see that you have the log base 7 of 7, but this is just the number of 2. Sorry, this should be a plus sign here. And then the log base 7 of 2 is 0.36, and you have a negative 1/3 here. So what you end up with is negative 1/3 times 2.36, which really just becomes about, can you make this actually divide and be clean and make it up? Well, let's see if we couldn't divide this out a little bit. 2.36 divided by 3. We're going to go a little old school division because it said to divide round to 2 decimal places. So this would be 0.7 with the 2 here, and then 8, and maybe 0.78 and 2/3. So really we'd be rounding it to about negative 0.79. So again, we were able to just approximate that using only what was given. Okay, next direction set, we're going to express as a log of a single number. So I like to think of these direction sets as squish. Bring everything together back. This is the opposite of what we've been doing. So example of this would be if I gave you a problem like the log of A minus the log of B plus the log of, let's do plus 2 times the log of C minus 3 times the log of D. If I squish these together, this would be the log of, okay, so we got an A in the numerator, divide by a B, but then times a C squared, and then divided by a d cubed. This would be the single expression. If that was too much of a leap for you, let's slide this down and just kind of sort of group together my pluses. Log of a plus, this would be the log of c squared, minus, I'm going to group together these as the log of b plus the log of d cubed. So I have my positives and my negatives all grouped together, and then you can see how that moves to become that expression. Sometimes these look a little bit different with numbers. If I have the log base 3 of x plus 1/2 the log base 3 of y plus a 3, I want to bring this to a single expression. First, I need everything to be log base 3's. So log base 3 of x plus log base 3 of y to the 1/2 plus 3 would actually be the log base 3 of something. It'd be the log base 3 of 27, because now 3 and the log base 3 of 27 are the same number. And now I can bring this all together. This would be, let's see, log base 3 of x times the square root of y, and then times 27, which I'll put the 27 out in front of that. So that would be combining it into a single logarithmic expression. You'll also see directions that say to simplify, and these can be a lot quicker than it seems. 2 times the log base 4 of 32 minus the log base 4 of 8. So again, we're just going to move everything to become a single logarithmic expression and see where that takes us. This is going to be the log base 4 of 32 squared. Then divide by means over 8. If I move everything into exponents, I have 32 is the same as 2 to the 5th squared over 2 to the 3rd. So this is the log base 4 of 2 to the 10th over 2 to the 3rd, which is the same as the log base 4 of 2 to the 7th. So 4 raised to some power is 2 to the 7th. We can actually figure out what that power is by using the strategy of setting this equal to some variable, and going 4 to that variable is equal to 2 to the 7th. 4 is the same as 2 squared, which means that 2 to the 2x is equal to 2 to the 7, or 2x is equal to 7, or x is equal to 7 halves. So 7 halves was the same thing that this would have to be. This whole thing would have to be equal to that x. So that whole thing simplifies to 7 halves. Now finally we move into the meat of all this, which are some solves. So a couple of different problem types you'll see here with solves. One of them is ones that have lots and lots of just little log expressions. The log base b of x equals 2 times the log base b of 4 minus 3 times the log base b of 3. On the left, I have the log base b of x is equal to the log base b of 4 squared minus the log base b of 3 cubed, or the log base b of x is equal to the log base b of, that'd be 4 squared over 3 cubed, that'd be 16/27. So really we just get x is equal to 16/27. Moving into another example, we have ones that have variables in them, so log base b, or variable expressions, so log base b of x minus 5 minus the log base b of a 2x plus 1 equals the log base b of 2. So I get the log base b of x minus 5 over 2x plus 1 equals the log base b of 2, which means that x minus 5 over 2x plus 1 has to equal 2, which means that x minus 5 equals 4x plus 2, or negative 3x is equal to, add that, you get 7, and x is equal to negative 7/3. Now we run into a tricky issue here, because if x is equal to negative 7/3, we may have an issue with domain. We have to check this and see if when I plug it into each of those, do I get the log of a negative number? Because we cannot take the log of a negative. And in fact, in that first one, you definitely do. Negative 7/3 minus 5 is a negative. So that means that's out and it's no solution. So you must check these. You can end up with solutions that we call extraneous, because by taking these and actually dividing them out, I divide out the negative, but in the original problem, x could not have been negative. Well, it couldn't. The expression can't be negative. Let me show another example of where this happens and gives you one that works and one that doesn't. 14 gives me log base 3 of x minus 1 plus the log base 2 of x minus 2 equals 3. So I'm going to make the, let's make them both log base 2s, otherwise this won't work. I'm going to make the left side combine and become the log base 2 of x squared minus 3x plus 2. And we're going to make the right side completely change to become a log expression, so that 3 is actually the log base 2 of 8. Remember, that's because 2 cubed equals 8. So I'm taking 2, raising it to the 3 to get to this 8. And that means that my equation becomes x squared minus 3x plus 2 equals 8, or x squared minus 3x minus 6 is equal to 0. And you can decide if you want to complete the square or do a quadratic formula on this. I suggest trying which one you feel you're weakest in. So because this is the way it is, I'm going to complete the square. Half of 3 is 3 halves. 3 halves squared is 9/4. So I'm adding a 9/4 to both sides. Then factoring the left side gives me an x minus 3 halves quantity squared is equal to 4 times 6 is 24 plus 9 is 33. So 33/4. And then I end up with x is equal to 3 plus or minus root 33 all over 2. And then I kind of come back and look at the original problem, where we want to figure out if any of these are going to run into some massive issues here. And we do get some, because if I look back at the original one, the 3 plus root 33 over 2, that's going to work out just fine. It's a positive number, it's plugging in. But the 3 minus root 33, think about root 33 as being somewhere near root 36 or root 25. It's a little bit bigger than 5, which means that this is going to be a number that's going to be about negative 1 point something, maybe. That is definitely not going to work right here. It's going to plug in and get you a negative, so that's out. And my solution should just be x is equal to 3 plus root 33 over 2. And then, let's see. I think that's all I might want to do with you. Okay, enjoy.